Alright everyone, sit back, relax, and let's untangle something powerful today, linked lists. Right? We can divide the list data structure into an array and a linked list. Right? What are the examples for an array? Arrays, stacks, keys, right? What are the examples for a linked list? Singly linked list, doubly linked list, circular linked list based on stacks and keys. What is an array? The array is a linear collection of data elements in which the elements are stored in consecutive memory locations, right? Consecutive refers to elements in a sequence that follow each other in uninterrupted order, differing by a fixed value. Consecutive means 1, 2, 3, 4, likewise, right? While declaring arrays, we have to specify the size of the array, like this, right? This is the size of the array, right? Which will restrict the number of elements that the array can store, right? For an example, if we declare an array as int marks 10, right? 10. Then the array can store a maximum of 10 data elements, right? We have 9 data elements. If our array size is 10, this is the index value, right? Now the size of the array is 10, right? After we declaring an array, we can't add anything into the array, right? Cannot store 11 or more than 10, right? We can't add anything right now. What are the advantages of an array? Let's discuss. You don't need to declare large number of variables individually like this, right? We can declare array like this: int marks 5, right? We can use this instead of this, right? What are the problems we have to face with this? Too many variables, hard to manage, difficult to process using loops, right? With this, it has one name, which is marks. We can access using index like this, right? Marks 0 and marks 1. 0 and 1 is 0 and 1 are indexes, right? Okay. It is much cleaner and scalable. The second advantage: variables are stored in contiguous memory. An array stores elements in continuous memory location like this, right? Consider this table memory representation, assuming each int is equal to 4 bytes, right? You can see each element is next to the previous, right? One addressed increases by 4 bytes. One address increases by 4 bytes, right? You can see these things, right? This makes access faster and predictable. Last advantage is the handling of large number of variables of same data type. Imagine storing marks for 100 students, right? Without array, we would need this, right? Very difficult to manage, right? With an array, int marks, you can do this, right? Now we can use a loop to calculate total, right? Like this, right? Now we can use a loop to calculate total. It is very simple and efficient, right? What are the limitations of an array? Let's discuss, right? First one, rigid structure means fixed size, right? Examples: once you declare an array, its size cannot be changed. This array can only store 5 elements, right? If you try to add one more like this, it gives errors. What are the problems in this case? You must decide the size in advance, and if you need more space later, you must create a new array. The second one, how to add or remove elements. Consider this. Arrays store elements in contiguous memory. So, inserting or deleting requires shifting elements. Think about inserting an element into original array, right? Insert 25 at index 2. How can we? Shift 30 to 40, 40 to 50. One position right. Okay. And after shifting, you can see this, right? 20, 25, 0, 1 and second index, right? This shifting makes insertion slow. Let's try removing an element. We wanna remove element at index 1, 0, 1, right? Again, shift elements left, like this. See? Okay. Next, cannot be dynamically resized in most traditional languages. In languages like C, arrays are fixed size. Now we want 5 elements. What should we do? We must create a new array, copy old elements, add new elements. This wastes time and memory. Just remember, modern languages like Python use dynamic lists internally, but basic arrays are fixed. The next one, memory loss, and also we can say memory wastage. This happens when we declare more space than needed. Example, consider this one, right? we declare this, but we only use these things, right? Remaining 97 spaces are unused. If each int takes 4 bytes, we have 100 space. Therefore, Therefore, 400 bytes are allocated, right? But we uses 12 bytes, right? You should multiply 3 by 4, right? Uses 12 bytes. Wasted, subtract 388. Oh, sorry. 12 is equal to 388, right? Wasted 388 bytes, right? That unused memory cannot be used for other variables, right? Linked list. It can store a collection of nodes connected together via links pointers. This is a node. These are connected using links, right? A node contains two things. First, data, and second, a link that connects it with another nodes. The first node is called the head node, right? And we can traverse the whole list using this head and next links. Also, we can say the cell for the node, right? Some value or data data structure is contained here, right? And nodes like these are connected in various ways to build a data structure. We can represent a linked list as a data structure like this. We can represent the connection between the item and the next item like this, right? Okay, we can represent backwards connections like this, but we need previous, right? How can we represent backwards? Like this, previous, and this to this. Next, we can represent next like this. Okay, forward and backward, right? Each element in a linked list is linked to the predecessor and successor nodes, right? This follows for more efficient insertion and deletion of nodes, right? Name this as the predecessor, which means the previous one, right? And this is the successor, this is the next one. Think this is like a child's pop chain. To insert this to the chain, take it and connect it to the back of the next piece of pop chain. Now we have a piece to insert to the middle of the chain. How can we do this? Inserting a new piece into the middle of chain involves merely breaking a connection like this, right? Breaking a connection, and reconnecting the chain at both ends of the new piece, right? And like this, okay. See, each item has a data part. We can say data, right? Data part and a link that points to the next item, right? Link. One natural way to implement the link is as a pointer, right? That is, the link is the address of the next item in the list. It makes good sense to view each item as an object, that is, as an instance of a class, right? We call that class as a node, right? The last item does not point to anything. We set its link member to none, right? This is the last item. We set its link member to none, right? Okay, this is denoted graphically by a self loop. Let's explain the difference between arrays and linked lists. Two fundamental data structures in computer science, right? An array has a fixed size, like this, right? This means once we define its size, we cannot change it easily. Because of this, arrays may sometimes waste the memory, right? If we don't use all the allocated spaces, right? Unlike arrays, linked lists have a dynamic size, right? This means they can grow or shrink during program execution, depending on our needs, right? Next one. In arrays, insertion and deletions are inefficient. Why? Because when we insert or remove an element, we usually need to shift other elements, right? We should, shift. Shift other elements to maintain order, right? This shifting process takes extra time, right? In linked lists, insertion and deletions are efficient. We don't need to shift elements. Instead, we just update the links or pointers between nodes, right? We just update links or pointers, right? This makes these operations faster compared to arrays, right? Let's meet from the next part of linked list. Until that moment, bye bye. Don't forget to subscribe us, like, comment and share with your friends. Bye bye.